In this video, we're going to continue to look at polyprotic acid calculations. We're going to look at how to calculate the concentrations for a strong polyprotic acid. So before you watch this video, be sure you look at the video showing you how to do calculations for a weak polyprotic acid. So let's take a look at a problem here. It says calculate the pH and the concentration of all species in a 0.10 molar sulfuric acid solution. Sulfuric acid is a strong acid, so the Ka1 is too large to measure, and we are given the Ka2. So before we get started, pause the video and see if you can write the dissociation steps for the first and second dissociation of sulfuric acid and the Ka expression for the second dissociation step. Pause the video and give it a try. Okay. So here's our first dissociation step. We have sulfuric acid and water, giving us hydronium and HSO4 minus. Now, since this is a strong acid, this completely dissociates. So really it's only a one-way reaction, and so the reverse reaction does not occur. So we can't write a dissociation, a Ka expression for the first step. The second step, we have HSO4, and that in water gives us some more hydronium and the sulfate ion. HSO4 is a weak acid, and so we're able to write a Ka expression for that, and you can see that here, and the value for Ka2 was given in our problem. So here we have our two dissociation equations. Just a couple of notes. Be sure to note that the hydronium is produced in both the first and the second steps. So when we're asked to calculate the pH, or our final hydronium concentration, we're going to have to take the sum of these two hydronium concentrations. And the HSO4 minus concentration, the final one, well, we're producing some of it in the first step, and we're going to lose a little bit of it in the second step. So our final will be what's produced in the first step minus any of that dissociates in our second dissociation step. So just be sure that you're aware of that before we begin our calculations. So let's begin to calculate. First, let's calculate the concentrations of the species produced in our first dissociation step. So I'm going to set up an ice table. Here we have our chemical equation for the first step. Our initial concentrations are entered. You can see those here. The change in equilibrium. Well, we know that since we don't have any HSO4 minus to begin with, our reaction must proceed from left to right. So our initial reactant concentration will decrease, and our initial product concentrations will increase by plus X. So we can figure out our equilibrium concentrations, but here this is a little easier. If you remember, of course, H2SO4 is a strong acid, which means it dissociates completely. So we know that our equilibrium concentration of the acid, the protonated acid, is 0. And since it dissociates completely, for every 1 mole of the acid that we start with, we're going to produce 1 mole of hydronium and 1 mole of HSO4, the conjugate base. So our equilibrium concentrations of these guys will both be 0.1 for our first dissociation step. So we don't have to go through any Ka expressions with this. Now let's move on to our second dissociation step. For our second dissociation step, let's set up an ice table. Here's the equation that we showed you earlier for the second dissociation step. Let's plug in our initial concentrations. So our initial concentration of HSO4 minus is 0.1, and we saw that from our first ice table. Hydronium is not 0, it's 0.1 because we have some of it, a fair amount of it, produced in our first step. Our sulfate ion concentration will be 0 initially. The direction, well, since our sulfate is 0, initially our reaction must go from left to right in order to produce some sulfate. So the changes will be minus X on the reactant side, plus X on the product side. Now our equilibrium concentrations here will be what we started with minus X, or what we started with initially plus X over on the product side. Let's set up an equilibrium or Ka expression for Ka2. You can see that here. And now let's plug in our values. Our Ka2 was given in the problem, and now we can plug in our equilibrium expressions, or excuse me, our equilibrium concentrations into our expression. Now let's solve for X. We can make the assumption that this minus X is probably negligible, or maybe negligible, compared to our initial concentration of HSO4 minus. So let's do that. Let's assume X is negligible in order to simplify our calculations. We would get this, and our 0.1s will cancel, so we'll get X is equal to 1.0 times 10 to the second. But we have to check to see if that assumption is valid. So to do that, we take our value of X and divide it by the initial concentration of HSO4 minus times 100. When we do that, we get 10%. The percentage must be less than 5% in order to make this assumption valid. So we could not say that X is negligible in this problem. And so we have to go back. Here we have our X, so we have to go back and solve it using our quadratic equation. So here you can see I've solved it. Be sure you take some time and go through the calculation. Don't just watch this, but you do it yourself and get this in the form of a quadratic equation. Okay. Our X value, or our A value would be 1, our B value would be 0.11, and our C value would be negative 1.0 times 10 to the minus 3. We can now plug these into our quadratic expression. You can see I've done that here, and solve. Pause the video and see if you can solve this, and then check your answers with what I have. So we should get two values for X. You can see those two values here, but only one of those values can be correct. Obviously, we can't have a negative concentration, so the negative 0.12 concentration cannot be valid. So our X value must be 8.4 times 10 to the minus 3. Let's plug that into our ICE table for X. We can plug it in here, over here, and here, and we should get our concentrations of HSO4 minus. You can see we get about 0.09, rounded to the correct sig figs. Our hydronium, here we have what we started with plus what we formed in our second dissociation step. So this was the first and this is the second. So this is my final hydronium ion concentration for the solution, or the total. My sulfate ion concentration, you can see that here, that's equal to X. Now we can take the pH of the solution based on this final hydronium ion concentration. Again, we need the total, not just that from the first or second dissociation step, but the sum of those two. So I take the negative log of 0.11 and I get a pH of 0.96. That's very low, but that's what we would expect with a strong acid. We can also calculate the hydroxide ion concentration by dividing Kw by hydronium ion concentration. And you can see we get the hydroxide 9.1 times 10 to the minus 14. So here's all of our concentrations. The sulfuric acid was 0. You can see all the others that we calculated. So be sure that you can recognize a strong polyprotic acid when you see one and solve it accordingly.